Hello, welcome to the to one of the bonus videos. I'm going to talk about a couple of intricacies about the variance operator that I didn't go into during the lecture. Okay, so I'm going to start with this statement. I said that variance is also equal to or can be computed using this expression, variance of a discrete random variable. And let's see how this is possible. And during this pretty much simple derivation, we're going to see a couple of things. We're going to understand a couple of things more truly related with probability, I guess. All right, let's start with variance of x. The definition is, in terms of expected variable, is actually x minus mu square, expected squared deviation from the mean value. And this is actually equal to, can be computed as x minus, here we have lowercase x minus the expected value, this deviation square weighted with respect to the probability mass function. Now I'm going to continue here. I'm going to just take the square here. So let's do that. This x square minus 2xm plus mu square, all weighted with respect to the probability mass function. Still very simple arithmetics. We just distribute fx. And now I'm going to write all of the summation signs separately. And up to this point, there should be no problem. Now, at this point, I'm going to concentrate here first in this expression. Now, in this expression, we should realize that this mu itself is a constant. At first sight, at the very beginning, for students, this may seem strange, but actually, mu has been already found using the expected value formulation. This expected value formulation is used on the distribution, and we come up with the result of mu. And once we find this, this is actually a constant now. This does not change with respect to x. Mu is here, does not change with respect to x. Which means here, since this is a summation with respect to x, you can take this out as a constant. And whatever I said here in terms of mu is also applicable here for mu square. So mu square also can be taken out. So therefore, we can write this whole expression as 2 is a constant also, mu x fx plus mu square fx. Now let's use the fundamental probability rules of probability. This quantity summation of the probability mass function over domain of x is going to be equal to 1. And this is going to be, note that x times fx is the expected value or mu of this distribution. Therefore, what we have here is x squared fx minus 2 mu square plus mu square. And these will be equal to minus mu square. So we got the expression that we need to prove. Here, the very same expression. And another point needs mentioning here. Note that this quantity is actually equal to expected value of x square. Why? Because if you recall, the expected value of any function can be found by using that function in the summation multiplied by the probability density function. So here the function is going to be expected here, x squared. Therefore, variance of x can be written as expected x squared, expected x squared. Although the pronunciation seems to be identical for these two terms, they are not. Note that the first term is the expectation of the squared x, whereas the second term is the expectation of x squared. So that's an important thing. So actually, that's why, I'm very sorry, square is written here, because when you write it here, as I said earlier, first squaring is performed, then expectation operation is performed. Therefore, the correct way of showing this is, maybe I should here. All right. I think this looks nicer. Expectation of the squared x minus expectation of x squared. If these values are both these two values are close to each other, variance and the spread of data is going to be small. The reason why this value is large is because x values, there are some extreme values or very small x values which very much deviates from the square of the mean value. That's another way of looking at the whole thing. Okay, so this was the first thing I would like to talk about. The second thing I would like to talk about is this proof. Prove that variance of ax plus b is equal to a square variance of x. Now, again, this is not for the sake of mathematical purposes only. I would like to demonstrate a couple of probabilistic or statistical tricks here that may be important. Okay, now note that here, note that A and B are constants. And when I say constant, again, remember that just like mu, this is a constant, right? So it's not a function of x. It may have nothing to do, but at least you may say that mu is derived from x. That's okay, but once it's derived, it's irrespective of x. Again, variance is similar. Once it's derived, it's irrespective of x. But maybe these have got nothing to do with x. But for the mathematical functions point of view, these are just constants, whether they are mu or variance or a, whatever. So now let's ax plus b here is going to be equal to, actually in terms of expected value, this is a plus b minus expected value of ax plus b here and square. Therefore, this is the quantity which we are interested. We subtract this quantity from its expected value. We square it and takes the expected value. Now, in the lecture, I have shown you that this expression is using the summation, in the summation formulation, this expression is actually equal to a times expected value of x plus b. Now, if we put this value here, if we replace this value, it's going to be equal to ax plus b minus a expected value of x minus b. And now b will cancel and we end up with this expression. All right, too many parentheses becomes a bit confusing. All right, now the interesting point here is this. During the lecture, if you like, you can go back to the lecture and listen again. The constant didn't appear in the last expression for the variance. Actually, since this is the proof, as you can see, and I try to explain it by saying that when you change the location of this new variable by adding b, you do not change the spread. And the mathematical reason is here. At this point, it becomes clear. Because we subtract from the expected value and that constant, which is irrespective of x, it is whether it is the x itself or its expected value, the constant affects the same amount, as the same amount, magnitude of effect. Therefore, when you subtract these to each other, from each other, these b will cancel and end up not being present in the formulation for variance. All right, but still this is not over. It's going to be, all right, we have some square here. Yeah. Now we are going to do this whole thing. So it's going to be expected a square. Well, either at this point you can take the square and do the whole thing, but I think it would be easier to show it in expectation operator. Now we have a function here, squared function. This function, we multiply, we weight it with respect to the probability mass function of x and add over domain of x. And let's go step one further. This is going to be a square x minus expected value of x. All right, I take the square and apply here. Since this is a constant, I take this out. And this is going to be a square x minus expected value of x. All right. Now, what else do we have here? Now, this formulation, you should realize that it is actually variance of x. Therefore, this is going to be equal to, well, even at this point, we could have employed the same thing. It would be equal to expected value of a square minus x minus expected value of x square. Then we could have taken e out. Ups. Up. All right, and this is again variance. We could have also shown it that way.